Okay, in section 8.4, we're going to look at sequences a little bit differently. So the I can statement is I can find sequences from tables and graphs. Tables and graphs. And again, can't forget these formulas. So what is the nth term formula for an arithmetic sequence? Again, the nth term is the first term plus n minus 1 common differences. And for a geometric sequence, the nth term is the first term times n minus 1 common ratios. And why do both of these formulas have the expression n minus 1 in them? Well, it's because of how many common differences or common ratios it takes to get from the first term to the nth term. And you remember in section 8.1 and 8.2 when we introduced arithmetic and geometric sequences, we talked about how many common differences or common ratios it takes to get from the first one to the nth one. And that's really where these formulas came from. And then it says, what are other names for the nth term formula of a sequence? So we can call them explicit formulas or general formulas. Explicit formulas or general formulas or nth term formulas, all the same thing. Now, we're familiar with arithmetic and geometric sequences, and it's important to be able to recognize these in a bunch of different settings. So we're going to look at the instructions for each one of these, for all these examples. So there are 4 parts of this, and you'll notice that we've got a table of numbers here, an XY table here. So it says, describe the operation used to go from one term to the next term in the sequence. Find the next missing term in the table. Tell whether the sequence is arithmetic, geometric, or neither. We are going to run into one that's not either one of those. And then write a general rule for the sequence. So we'll only focus on a general rule for right now. And if we need to do some others down the road, then we will. Now remember, unless we're told otherwise, the index starts at 1. So what we're going to do is we're going to key off the ordered pair in here. So we've got a whole bunch of ordered pairs here, but what we're going to key off on is we're going to key off the one with an x is equal to 1, because this is going to be like the first term, this is the second term, this is the third term, and this would be kind of like going back in time. All right, so let's see, to find the next term on this, so let's go ahead and take a look at this. The first term is 8, then 11. So there are lots of ways to get from 8 to 11, but let's just back up and see if we can tell what goes on here before this first term. So we've got a 2, then a 5, then an 8, then an 11. So let's see, if we subtract here, this would give us 3. Subtract here, this would give us 3. So I think we're going up by 3 every single time. So what we do is we add 3. So let's just write add 3. So that would make this next one 14 right here. So the next term in the table would be 14. And remember, if we're adding the same thing every time, then this is going to be arithmetic. And let's write down a general rule for this. So this is going to be a sub n is equal to the first one, which is 8, plus n minus 1 common differences of 3. And then we'll distribute through, so we get, let me just shorten this up here. We're going to have an 8 plus 3n minus 3, thinking ahead to the answer here. So this is 3n plus 5. So the general formula is a sub n is equal to, what have we got here? 3n plus 5. So that right there is what will determine the whole thing for us. So we're going to come down here, and let's take a look at the next one. So we've got 0.5 or a half, and then a 1, and then a 2, and then a 4. So this one, it kind of looks like it's doubling every time, or we could do this. Take any term and divide by the one before it. 1 divided by 0.5 is 2. 2 divided by the one before it is going to be a 2. 4 divided by the one before it, that's going to be a 2. So what's happening here is we're doubling every single time. So this is going to be an 8. So the next term in the table is an 8. So to get from one to the next, you multiply. So let's say multiply by 2. And then arithmetic or geometric, well, if we're multiplying from one term to the next, then it's geometric. And a general rule here. So we're going to have a sub n equals, it's the first term, and again, we're keying off this one right here, so this is the first one, is a 2, and then the common ratio is 2, and then to the n minus 1. And again, cleaning this up here, we've done this quite a bit here. So this is 2 to the negative 1. That's going to make this a 1/2 out front. Those are going to cancel. So that means a sub n is going to be 2 to the n. So general rule is a sub n equals 2 to the n. And just to double check and make sure that that actually works here, let's plug in a 1. If you plug in a 1, that's 2 to the first, that's a 2. If you plug in a 2, that's 2 to the second, that's 4. If you plug in a 3, there we go, and we're all set. Now, one thing that we could do with this is we could take this and we could just put this formula in here and we could say, okay, this is 3n plus 5. So if you know what the index is, you just plug it in right here. And on this one, we could plug it in right here and we could say, okay, this is going to be, if this is n, this is 2 to the n. And then do you notice anything about the general formulas, the numbers in the general formulas, and some of the numbers in the table? So if we take a look at this right here, we've got a 2. Well, there's a 2 right there. And if we take a look at this one right here, we've got a 5 and a 3. So I don't really see any 3s other than the, oh, there's a 3. But the common difference is 3, but there is a 5 right there. Okay, so just kind of keep that in mind as we go through here. And we're going to take a look at this example right here. This one has an asterisk by it, so there's probably something different about this one. It says, how do you find the next term? What's the next term in the table? So all those common questions. And let's take a look here. So we start off with 0 and then a 1. So the first term is 1. Again, we're keying off this one right here. So this would be a sub 1. This would be the first term here. So 1, then 4. So we'd go up by 3 if we were adding something, and we'd times by 4. But then we go up by 5, so that's not the same common difference. And to get from 4 to 9 by multiplication, that would be timesing by 2 and a fourth. So that's a little bit messy. So let's see if we can find out what's going on here. Let's see if we can find a relationship between each one of these. If we've got a 1, if that's our index, we get a 1. If we have a 2, we get a 4. If we have a 3, we get a 9. And if we have a 4, we get a 16. And then the question is, well, what if we plug in a 5 into whatever this rule is? Well, it's definitely not arithmetic or geometric because we don't have a common difference or a common ratio. So that one's neither. So could we figure out how to get that next term? Do you notice anything about those numbers? Those numbers should look kind of familiar. The next one is a 25. So to get the next term, you actually square the index. So to find the next term, you square the index. And in this case, the index is the x value in the table. So the next term in this table is a 25. And then the general formula, which we'd put right here, well, if you just square the index, then this would be n squared. So a sub n would be n squared. Now, the reason this has an asterisk by it is because we don't study sequences like this very much, but it is possible to have sequences that don't follow either one of the rules that we've talked about, arithmetic or geometric. So let's take a look at the other side. Okay, we're on the other side, and we're going to start with points on the graph, and that's really no different because all the points are here is a different way of writing down an XY table. So this point right here is 1, negative 1. This point right here is 2, 1. So instead of having these organized in a table, we've got these organized in a graph. So I'm going to start right here. This is 4, 5. This is 3, 3. This is 2, 1. This is 1, negative 1. This is 0, negative 3, and this would be negative 1, negative 5. So what we're keying off right here is this one right here. So this is the first term in the sequence. So it's negative 1. The second term is 1. The third term is 3. And then the fourth term is 5. So let's take a look at these. Negative 1, then 3, then 5. So it might actually be a little bit easier to identify what's going on here because take a look at this. Every time we go from this term to the next term, we go up 2. Up 2 to get to the next term, up 2 to get to the next term. So it looks pretty kind of like a linear graph, which is what shape that is. And this rate right here, this slope, if you want to think of it that way, that is our common difference. So to go from this one to this one, you add 2, you add 2, you add 2. So this is arithmetic. And an nth term formula for this would be, okay, so we've got to do a sub n is the first term, which is negative 1, plus n minus 1 times the common difference. This common difference is 2. So we're going to times by 2, distribute that through, 2n. This is going to be a minus 2. Put those two together. So a sub n is equal to 2n minus 3. And there would be our formula right there. Okay, so we're going to come down here and we're going to take a look at this next one. And we're going to do the same type of thing. And you can tell from the shape right here that there's definitely something different going on. So this shape right here, unlike the one up above that kind of looked like a line, this one is definitely exponential, okay? Because it kind of starts here and then goes up like that. It's got that big bend, that big growth curve to it right there. So let's see what happens here. This one right here is the first one. So this is 1, 6. This is 2, 12. This is 0, 3, and this is -1, that's about 1.5. Okay, so we're going to do 3 halves. Okay, so let's think about what's happening here. It used to be 1/2, and now it's 3, and then it's 6, and then it's 12. So it looks like what's happening, if I were to take any one of these y coordinates, 12, and divide by the y coordinate before it, we end up with a 2. 6 divided by 3 is 2. And take a look at this. This is 3 divided by 3 halves. We never divide by a fraction, so I'm going to flip this over, cancel those, so we end up with a 2. So this is geometric, definitely geometric. And let's do an nth term formula here. So we'll do a sub n is equal to the first term right here, 6. And then the common ratio is 2 to the n minus 1. So we're going to have a 6. Let's see, times 2 to the n times 2 to the -1. This becomes the reciprocal, so this is going to be a 1/2. So I'm going to go ahead and simplify this. The 2 is going to cancel with the 6. This is going to be a 3 times 2 to the n. So this right here is our formula. So we're going to write a sub n is equal to, let's see, what have we got here? 3 times 2 raised to the n. And if we wanted to, we could put that in parentheses and make it look like that's the ratio there. Okay? All right. Now, I'm going to shrink this down just a little bit because we want to talk about this. Do you notice anything? We talked about this on the previous page. Do you notice anything about the numbers in the formulas and the numbers on the graph? So we want to point something out. We figured out that the common difference here was 2. So I'm going to write a big D equals 2 on here. Okay? And on this one, we're going to write R equals 2. So we can see that. And then I want you to notice that that 2 showed up in here, and then there's a -3. Well, where is there a -3 as far as this goes? Well, it's right here. It's like the y-intercept. It's like the 0 term. It's not the first term, but the one right before the first term. And then let's take a look at this formula down here, the one for the geometric one. Where is there a 3? There's a 3 right here, kind of like that y-intercept up above there, kind of like the 0 term, the 0th term if you want to talk about it that way. And then 2 is the common ratio. So that actually gives us a way that we can figure out what the equation is without doing a bunch of really nasty work like we did here and simplifying and all of that sort of stuff. So if you notice something about one particular point on the tables and on the graph, you might be able to come up with an nth term formula of an arithmetic or geometric formula very quickly. So let's see if we can identify what's going on here. Again, this is what we keyed off usually. It was the first term. But you'll notice that this 0th term, the one right before it, actually shows up in the formula. So that right there, 0, 3, that 3 goes right there, and then the common ratio goes there, and then it's just to the nth power. And on this one, -3 is the y-intercept, so that goes right there. And then the rate, kind of that slope, that common difference, that ends up being right in front of the n. And let's see if that same thing holds over here. So on this one, on example number 1, remember we decided that this was arithmetic, so it went up by the same amount every time. There's 3, and then notice that the y-intercept, 0, 5, that 5 goes right there. Now, this one is a little bit tricky to take a look at on example number 2 because the y-intercept would be right here. It would be 0, 1. Well, like we said on the other side, that y-intercept, 3, goes right in front of the common ratio raised to the n power. So let's come back over here and take a look at this. This is the y-intercept. That's the common ratio. But watch what happens if you put a 1 in front of it. It doesn't change anything. So I'm going to come back over here, and let's talk about how we can do these in a much more concise way, a little bit quicker fashion here. So I'm going to go ahead and expand this out again. So we can use a0 to represent the y-intercept. So let's put a y right here. A0 is sometimes referred to the initial value. In other words, it's what we get when we plug in a 0. Like we've just started the stopwatch. We haven't really done anything yet. We haven't even gotten to the first term. We just started right here, and then to get to the first term, you do, whether it's a common difference or a common ratio. So once we have that figured out, then we've got a really quick way to write down the formulas. So for an arithmetic one, the nth one is going to be d right here. So this is going to be the common difference. So if you find the common difference, you just put that right in front of the n. And then whatever the y-intercept is, or whatever the 0th term is, you put that right here. So the y-intercept, we're going to call that a naught. So this one right here, again, y-intercept a naught, and then this is going to be the common ratio. So we still have to figure out whether it's a common ratio or common difference, whether it's arithmetic or geometric. So here's the bottom line. When we deal with arithmetic sequences, they are a lot like a linear function. So take a look at this. This is like mx plus b here. So this is a lot like a linear function. We figure out what the slope is and what the y-intercept is. But we just have discrete values that are given when we plug in a 1 and a 2 and a 3. So first term, second term, third term, and so forth. And a geometric sequence is like an exponential function whose discrete values are given when we plug in a 1, 2, and 3. So first term, second term, third term, and so forth. So you can see the geometric is exponential, and you can see that the arithmetic is linear. So it's kind of like having f of x equals mx plus b over here. And on this one, it would be f of x is equal to, we'd have like an initial value, and then we'd have b to the x. So it would look something like that, and I'll just put an a naught right there for the initial value there. Okay, this is again a relatively short section. We put the ideas together, piece them together. In the next one, we're gonna apply these into real world situations. But this is a great section. Study hard. If you've got questions, please ask.